So we already had 3 talks out of 5, essentially, that talk about mixed data. So I think this gives you kind of like the importance of this open question is like, okay, we've been doing like causal discovery for a long time now, but in real problems, data are not all continuous or all discrete. So we need to do something about that, and I think the roster today of talks illustrates that. Then also another thing illustrated, I think, is the emphasis on learning models from with latent variables. So that was also the topic of the previous talk. It's also the topic of my talk, which is done by my student Konstantinos Tsirilis, who couldn't be here today. So some of these things have been already covered by other speakers. And the main problem here, again, is going to be to learn models like maximal ancestral graphs from data in the presence and admitting the presence of latent variables, and particularly variables that can be causing 2 or more observed variables, or as we call them, latent confounders. We'll present the algorithm that we propose and then compare it against a couple of alternatives in the literature, one of which is the CFCI that was just discussed just now. So the problem of learning the structure is to induce the graph or a set of graphs that best describes the dependencies between the variables in the given data set. And as I mentioned, we make the causal Markov condition and the faithfulness condition assumptions. Okay, now we've talked about Bayesian networks, which don't really admit latent confounders. They assume we observe all confounding variables. And the nodes, the edges denote direct causal relationships. But they have been extended to the cases where we may have latent confounders, to this type of models that are called maximal ancestral graphs, or MAGs for short. That's another acronym in today's talks. That is an extension of the Bayesian networks and allows the modeling of cases that are called causal insufficient cases, where you may have latent confounders. So in this type of graphs, you'll see bidirectional edges in addition to directional edges, in addition to this one that means X is causing Z, causally affects Z. The bidirected edges mean that there is a latent confounder that causes both X and Y simultaneously. And neither X causes Y nor Y causes X. Okay, that's what the bidirectional edge means. Okay, so the thing is that our data may be fit equally well by a number of models with latent variables. And each one could be represented with a maximal ancestral graph. Here we would put a bidirected edge. Here we would put another bidirected edge. And there's a new type of a graph called PAG that captures all of the equivalent networks. You see the edges are present or absent whenever all equivalent networks have a present or absent edge. And the endpoints have an arrow whenever there's a X3 is not an ancestor of X1, and a circle when we are uncertain. So this circle could be an edge, meaning that there's a latent confounder between the 2 variables, or it could be nothing. It could be a tail, which means that X1 is causing X3. So this circle is our uncertainty about what's the true nature of the edge. All right, so in order to learn this type of models, which may I say are much more realistic than Bayesian networks, people have been using Bayesian networks forgetting that they make the assumption that they don't admit latent confounders, and they may totally mislead practitioners with implausible causal edges. So these are more realistic types of networks, making fewer assumptions, less strict. They're causal constraint-based methods that depend on condition-dependence tests. I described them like earlier. And there are score-based methods, which was also discussed in the talk about for scoring Bayesian networks of mixed variables. And the difference is here we perform condition-dependence tests, and based on the results, we try to induce a network. Here, we search in the space of all possible networks, trying and score each one of them, how well they fit to the data, trying to find the best scoring network. And then we have hybrid methods that they try to combine the two approaches. Usually up to now, learning maths was done with constraint-based methods because we just didn't know how to score these networks with latent variables. But quite recently, actually, 2 years ago, there was a way to score networks, MAGs, with continuous variables only. And the next year, we incorporated this scoring method into a search and score algorithm in a publication with my former student, Sofia Triandafilou. And it worked quite well and was very competitive with constraint-based methods. So now we're trying to actually go further and even scale up and improve better the performance of this method by combining it with, making it hybrid and combine it with constraint-based methods. We did the same with an algorithm that we introduced in around 2006 called MaxMin hill climbing, which was a hybrid method. The new approach is along this same lines. So in 2006, we introduced the network for this algorithm for Bayesian networks. And it works with, it's a hybrid method, works in 2 phases. In the first phase, it tries to identify the skeleton using tests of independence. So it's a constraint-based, this phase. And once you learn the skeleton, it runs a search and score method to do the orientations. But the trick is that the search and score that we do afterwards, it's constrained to only add edges that were found during the skeleton phase. So it doesn't try to add any edge. The search is constrained by what you found in the previous phase. And that seemed to work very, very well. Back in 2006, this was one of the best algorithms to learn Bayesian networks. It was scaling up to like tens of thousands of variables and so forth. So the idea is like, can we do something like this for this richer class of models like MAGs? So intuitively, why does it work best? Well, when you perform tests of condition independence, you can quickly and quite reliably sort out what edges are in the network. And you get the skeleton well and quite fast. But it turns out that score-based methods are much better, in my opinion, in my experience, in orientations and in orienting and finding colliders. So when we combine the two, I think this is why we got like good results. Yes. All right, so now what we do again the same trick, which is like in the skeleton identification phase, again, we run MMPC, the MMPC algorithm to find the parents and children of each node. And then we have a search and score phase that is constrained by only the edges that were found during the skeleton identification phase. But this time, the scoring, of course, has to be applied to MAGs. And that's the main difference from the original algorithm. So how does the scoring works? Well, we start with the empty graph. And then you try to apply a number of operators like add edge or reverse edge or remove edge and so forth, score all the derivative networks, and commit to make the change in your network that increases the score the best. Okay? So let's see. Yes. Maybe I'll go up on the podium. Click. Okay. Where is it? All right. So scoring a MAG is much more involved and complicated than scoring a Bayesian network, and it has only been solved so far with continuous data. So there are big open problems how to do this with mixed types of data. So in the big score of a graph is the log likelihood of the data given the graph plus a penalty based on the parameters. And in 2015, it was demonstrated that this likelihood score can be decomposed according to what is called the C components of the graph. The C components of the graph correspond to nodes that are connected through bidirected edges. So here's an example. These are the C components. V1 is not connected to anything by a bidirected edge. Neither is V2, so they form their separate C components. But these three edges are connected through paths that go through a path with bidirected edges, and they form their own C components. So we have three C components here, and the log likelihood of the data is the sum over all components. And this formula can be used, I mean, that's the main result, I guess, one of the main results of the papers, that this formula can be used to score the likelihood of each component individually. Okay, so by using this, we can actually score a MAG. Now, the next thing is to perform a greedy search. We start with the empty graph. Let's suppose at some point we reach this graph, and now we can apply certain operators like orient this edge as bidirected instead of directed, or remove an edge, add an edge, and so forth, resulting in many derivative networks. And as you can see, the branching factor when you do this search and score is really large for MAGs, much larger than when you're searching for Bayesian networks. Now, at each step for each one of these nodes, we need to compute the score again. And if you do it naively, the algorithm is going to take a really long time. So to do it a bit better, you need to recompute the score only for the connected components that actually change. And in order to do that, you need to be, essentially when you add the bidirected edge, you create new components. And you need to be careful how to do this, how to cache results and only to compute what you need to. And that's what we did last year in this presentation, in this publication, I'm sorry. Now, the idea is that to reduce the branching factor here, we run the skeleton identification phase in the previous step, and we only apply operators that work with edges that have been found in the skeleton identification stage. That is the constraint greedy search. Okay, so we compare this strategy with the previous algorithm, the greedy search, that doesn't constrain the search with constraint-based methods. With FCI, that is a prototypical, probably the first and one of the best algorithms around, and conservative FCI that we heard about before. There are other competitors also. One of the ones we really want to compare against, and it looks very prominent, serious competitors, is GFCI. Oops. Okay. There's, can you, there's something something appeared here.
So I should turn the internet off. Yeah.
Okay. All right, so for the experimentation with simulated results, so that we know the true graph to compare against, we set the maximum conditioning set to 10 and computed 6 different metrics of performance. One is the structural Hamming distance and the running time. I explained the structural Hamming distance before. It is the error, it expresses error in reconstruction of the graph. The lower, the better. But also the structural Hamming distance is broken down to precision recall of the edges and of the orientations. So first, comparing with the greedy search. So this algorithm is doing a greedy search, but is restricted. And this algorithm does an unrestricted greedy search. And the results are pretty clear. I mean, we can focus on these first 2 graphs, which is the structural Hamming distance and the running time, and the rest is precision recall, which essentially break down the type of errors made. And out of which it's clear that the greedy search without any constraints is dominated both in terms of the error and in terms of the execution time by MMMHC. Okay, so it looks like constraining the greedy search not only gives you better results, but also improves speeding time. So that looks like a promising type of algorithm and ideas to combine both constraint-based as well as search and score methods. Then we compare it against the conservative FCI on randomly generated graphs, keeping out 10% or 30% of variables as latent. And here are the results. Again, focusing on the first 2 graphs, we can see that the quality of reconstruction is much better for the new algorithm, for the proposed algorithm, although the scalability goes down quite a bit, like once you start increasing the variable size. So you see that the green line here, which is FCI and CFCI, are basically scale up well and easily, relatively easily to 800 variables, but the new method doesn't scale up so well. So if my suggestion would be that if you actually care about quality of reconstruction, you should run the new algorithm if that is possible given your computational resources. And the same is true for when you have 30% latent variables. The next set of experiments, we actually experimented with causal networks that are available, that are created by domain experts. So they're probably more realistic than randomly generated networks. And in this case, these networks are called Munin, and the insurance network that I actually used as a running example in the talk, the first talk in the morning. And the results essentially that we get are qualitatively similar in terms of reconstruction error for the non-random networks, the networks created by domain experts. But an interesting observation is that in the in these networks, the difference in the running time goes down by quite a bit. So basically, with the random networks with 800 variables, CFCI is 200 times faster, but with these networks, it's only, let's say, 2 times faster. So it seems that these networks have actually structure that makes the difference in the execution time much less. So in conclusion, we introduced this novel algorithm that can deal with latent confounders, and we contrasted against some other alternatives in the literature, the prototypical FCI, an improvement which is more conservative, the conservative FCI, as well as the algorithm that we introduced last year, which is the unrestricted search and score, greedy search and score, and it performs better in terms of quality than all of them, and certainly faster than the greedy, unconstrained search. I think a major limitation of our algorithm right now is that it works only with continuous data. So I think a very important open research direction is how we can score mugs that way with mixed data. So, and I hope we can actually solve this, or someone can solve this, like in the next few years. Okay, well, thank you very much. I'm ready to take your questions.